Joint definition in geology. In geology, a joint refers to a fracture or crack in a rock mass along which there has been no significant movement parallel to the fracture plane. These fractures occur due to stresses within the Earth's crust, often as a result of tectonic forces, and they can vary in size and orientation. Joints are distinct from faults in that there is no measurable displacement across the fracture surface. Instead, they represent zones of weakness where the rock has fractured but not moved relative to each other. Joints play a crucial role in various geological processes and have significant implications for both the physical properties of rocks and the movement of fluids within the Earth's crust. They commonly influence the weathering and erosion of rock formations, as they provide pathways for water to penetrate and alter the rock mass. Over time, this can lead to the development of characteristic landforms such as joint-controlled valleys and cliffs. Moreover, joints can have important engineering implications, particularly in the construction of tunnels, dams, and other infrastructure projects. Understanding the orientation and spacing of joints in rock masses is essential for assessing their stability and designing appropriate support systems to mitigate the risk of rockfall or collapse. Geologists study joints through various methods, including field mapping, remote sensing techniques, and laboratory analysis of rock samples. By examining the geometry, distribution, and mechanical properties of joints, researchers can gain insights into the deformation history of the Earth's crust, as well as the potential risks associated with geological hazards such as earthquakes and landslides. In summary, joints in geology represent fractures in rock formations that have undergone no significant displacement along the fracture plane. They are important features that influence the behavior of rock masses, the movement of fluids within the Earth's crust, and the stability of geological structures. Understanding joints is essential for various geological and engineering applications, ranging from landscape evolution to infrastructure development and hazard assessment. Formation of joint. The formation of joints in geological formations is a complex process influenced by a multitude of factors, including tectonic forces, lithology, rock type and composition, stress regime, and the geological history of an area. These fractures can develop at various scales, from microscopic cracks to large-scale fractures spanning kilometers. Understanding the formation of joints requires consideration of both the mechanical properties of rocks and the dynamic forces acting on the Earth's crust over time. Tectonic forces, such as compression, tension, and shear, play a fundamental role in the formation of joints. These forces result from the movement of tectonic plates and the interaction of lithospheric plates at plate boundaries. Compression leads to the development of tensional joints, where rocks are pulled apart, creating fractures perpendicular to the direction of maximum stress. Conversely, extensional forces can produce joints oriented parallel to the direction of maximum stress. Shear stresses, occurring when rocks slide past each other horizontally, can generate shear joints, characterized by oblique or diagonal fractures. Additionally, the mechanical properties of rocks influence the formation and orientation of joints. Brittle rocks, such as granite and basalt, tend to fracture under relatively low stress, forming well-defined joints with sharp angles. In contrast, ductile rocks, like shale and gneiss, deform plastically under high stress, resulting in folding and faulting rather than jointing. However, even ductile rocks can develop joints under specific conditions, such as during periods of rapid uplift and erosion when overlying pressure is released. The presence of pre-existing weaknesses, such as bedding planes, foliation, or earlier fractures, can also influence joint formation. These discontinuities provide zones of reduced cohesion where fractures are more likely to propagate when subjected to stress. Furthermore, the orientation and spacing of joints within a rock mass are influenced by the regional stress field, with joints often forming in response to the orientation of principal stresses. Over time, geological processes such as weathering, erosion, and diagenesis can modify existing joints and create new ones. Weathering agents such as water, ice, and chemical reactions can widen existing fractures through physical and chemical breakdown of rock material, ultimately contributing to the development of joint-controlled landforms like canyons, arches, and caves. In summary, the formation of joints in geological formations is a complex interplay of tectonic forces, rock properties, pre-existing weaknesses, and geological processes. Understanding the mechanisms behind joint formation is essential for interpreting the deformation history of Earth's crust, assessing geological hazards, and predicting the behavior of rock masses in engineering and environmental applications. Types of joint. Joints in geology manifest in a variety of forms, reflecting the diverse geological processes and conditions under which they form. These structural features can be categorized based on various criteria such as their geometry, orientation, and mode of formation. Here, we delve into the different types of joints observed in geological settings, providing a comprehensive overview of their characteristics and significance. Tensional joints, also known as extensional joints, tensional joints form when rocks are subjected to tensile stresses, causing them to pull apart. These fractures typically occur perpendicular to the direction of maximum stress and are characterized by opening or widening of the fracture aperture. Tensional joints are common in regions experiencing crustal extension, such as rift zones and divergent plate boundaries. Shear joints develop in response to lateral movement along a fault plane, resulting in a horizontal displacement of rock masses. These fractures have an oblique or diagonal orientation and are typically associated with strike-slip faults and zones of intense shear deformation. Shear joints can exhibit complex geometries, including slickensides and polished surfaces indicative of past movement. Compressional joints form under compressive stresses, where rocks are squeezed together, leading to the development of fractures perpendicular to the direction of maximum compression. These joints often occur in regions experiencing crustal compression, such as convergent plate boundaries and mountain belts. Compressional joints are characterized by closed fractures and may display evidence of folding and deformation. Columnar joints are geometrically regular fractures that develop in igneous rocks, particularly volcanic and intrusive formations, during cooling and contraction. These joints typically exhibit polygonal shapes, with columns arranged in hexagonal or pentagonal patterns. Columnar jointing is commonly observed in basaltic lava flows and volcanic necks, where rapid cooling results in the formation of vertically oriented columns. Radial joints originate from a central point and radiate outward in multiple directions, resembling spokes on a wheel. These fractures often occur around intrusive features such as igneous intrusions, volcanic plugs, and domes, where thermal expansion or stress concentrations lead to the development of radial fractures. Radial joints are commonly observed in volcanic necks, laccoliths, and diatremes. Bedding joints, also referred to as stratification joints, form parallel to the bedding planes or layering within sedimentary rocks. These fractures result from differential compaction, erosion, or tectonic stresses acting perpendicular to the sedimentary layers. Bedding joints play a crucial role in the weathering and erosion of sedimentary formations, influencing the development of cliffs, benches, and other landforms. Fault parallel joints, also known as conjugate joints, occur parallel to existing faults or shear zones, reflecting the orientation of the principal stress field. These fractures form in response to the reactivation or adjustment of pre-existing fault systems, accommodating differential movement along the fault plane. Fault parallel joints are important indicators of structural deformation and strain partitioning within the Earth's crust. Diagonal joints exhibit oblique orientations relative to the regional stress field and do not align with any specific tectonic feature or structural trend. These fractures may develop in response to local stress concentrations, rotational deformation, or complex strain patterns within a rock mass. Diagonal joints are often observed in areas of geological complexity, where multiple tectonic forces act concurrently. Overall, the classification of joints in geology is multifaceted, reflecting the diverse mechanisms and conditions governing their formation. By identifying and characterizing different types of joints, geologists gain valuable insights into the deformation history, tectonic evolution, and mechanical behavior of Earth's crust, enhancing our understanding of geological processes and hazards. Classification of joints. The classification of joints in geology encompasses a broad spectrum of criteria, including their geometry, orientation, mode of formation, and relationship to geological structures. By categorizing joints based on these characteristics, geologists can better understand the processes driving their formation, as well as their significance in geological settings. Here, we explore in detail the various classifications of joints. Geometry-based classification. Planar joints. These joints are characterized by flat fracture surfaces that extend over considerable distances. Planar joints include bedding joints in sedimentary rocks and foliation joints in metamorphic rocks, which develop parallel to the layering or foliation planes. Curved joints. Curved joints exhibit non-planar surfaces, often forming arcuate or irregular fractures within rock masses. These joints may result from bending or flexural deformation, differential compaction, or localized stress concentrations. Orientation-based classification. Orthogonal joints. Orthogonal joints intersect each other at approximately right angles, forming a grid-like pattern within rock masses. These joints commonly result from isotropic stress conditions or mechanical layering in sedimentary sequences. Oblique joints. Oblique joints have orientations that deviate from perpendicular angles, intersecting at acute or obtuse angles. The formation of oblique joints may be influenced by non-uniform stress distributions, rotational deformation, or structural complexities within the rock mass. Mode of formation-based classification. Tectonic joints. Tectonic joints form in response to regional or local tectonic stresses acting on the Earth's crust. These fractures reflect the deformational history of a region and are often oriented parallel or perpendicular to major structural features such as faults, folds, and shear zones. Diagenetic joints. Diagenetic joints develop during the early stages of rock formation, primarily as a result of compaction, cementation, and chemical alteration of sediments. These joints are commonly observed in sedimentary rocks and may influence fluid flow and reservoir properties in hydrocarbon reservoirs. Relationship to geological structures. Conjugate joints. Conjugate joints are sets of parallel fractures oriented at oblique angles to each other, forming conjugate sets within rock masses. These joints indicate the orientation of principal stresses and the structural regime governing deformation within the Earth's crust. Joint systems. Joint systems refer to interconnected networks of fractures within a rock mass, comprising multiple joint sets with distinct orientations and geometries. The spatial arrangement and interplay of joint systems play a critical role in controlling the mechanical behavior, permeability, and weathering susceptibility of rocks. Scale-based classification. Macroscopic joints. Macroscopic joints are visible to the naked eye and typically extend over meters to kilometers in length. These fractures are important for structural analysis, geological mapping, and engineering geology assessments. Microscopic joints. Microscopic joints are fractures that are only observable at the microscopic scale, requiring magnification to be detected. These joints may result from localized stress concentrations, crystallographic defects, or mineral reactions during diagenesis and metamorphism. Rock type-based classification. Igneous joints. Igneous joints form in igneous rocks, including volcanic and plutonic formations, as a result of cooling and contraction processes. Columnar jointing in basaltic lava flows and hexagonal jointing in granite intrusions are common examples. Sedimentary joints. Sedimentary joints occur in sedimentary rocks due to compaction, cementation, and tectonic stresses acting during or after deposition. Bedding joints and stylolites are prominent examples found in sedimentary sequences. Metamorphic joints. Metamorphic joints develop in metamorphic rocks as a result of recrystallization, deformation, and regional metamorphism. These joints may exhibit foliation parallel or foliation crosscutting orientations, reflecting the structural evolution of metamorphic terrains. By considering these diverse classifications, geologists can gain deeper insights into the origin, evolution, and mechanical behavior of joints within Earth's crust, contributing to our understanding of geological processes, structural geology, and the interpretation of geological maps and cross-sections. Consideration of joints. The consideration of joints in geology is essential for understanding various aspects of Earth's crust, including its deformation history, mechanical behavior, fluid flow pathways, and landscape evolution. Geologists and engineers analyze joints in detail to assess their impact on geological structures, natural hazards, and human activities. Here, we explore the multifaceted considerations associated with joints. Structural geology and tectonics. Joints provide valuable information about the stress regime, strain distribution, and deformation history of geological formations. By analyzing the orientation, spacing, and geometry of joints, geologists can reconstruct the tectonic evolution of regions, identify active fault systems, and delineate structural trends. Joint patterns and distributions reflect the interplay of tectonic forces, including compression, tension, and shear, acting on the Earth's crust. Studying joints aids in deciphering the kinematics of faulting, folding, and fracturing associated with plate movements, mountain building, and basin formation. Engineering geology and geotechnical engineering. Joints significantly influence the stability and mechanical properties of rock masses in engineering projects such as tunnels, dams, slopes, and foundations. Understanding the orientation, spacing, and persistence of joints is crucial for assessing rock mass strength, deformation behavior, and risk of slope instability or rockfall. Geotechnical engineers evaluate the shear strength, cohesion, and permeability of jointed rock masses using field mapping, laboratory testing, and numerical modeling techniques. Incorporating joint data into engineering design helps optimize construction methods, support systems, and risk mitigation measures. Hydrogeology and groundwater flow. Joints serve as preferential pathways for groundwater flow and fluid migration within the subsurface. The interconnected network of fractures facilitates the movement of water, gases, and contaminants through the rock mass, influencing aquifer recharge, discharge, and contaminant transport. Hydrogeologists assess the permeability, porosity, and connectivity of joint systems to model groundwater flow dynamics, delineate groundwater recharge zones, and identify potential sources of groundwater contamination. Understanding how joints control fluid flow is essential for managing water resources and mitigating environmental impacts. Natural hazards and risk assessment. Joints play a critical role in the occurrence of geological hazards such as earthquakes, landslides, and rockfalls. Weaknesses along joint planes can act as nucleation points for faulting, fracturing, and mass movements, amplifying the severity of hazardous events. Geoscientists utilize geological mapping, remote sensing, and geophysical surveys to identify areas prone to joint-related hazards and assess their susceptibility to seismic activity, slope instability, and rock slope failure. Incorporating joint data into hazard maps and risk models enhances disaster preparedness and emergency response planning. Environmental geology and landscape evolution. Joints influence the weathering, erosion, and geomorphological evolution of landscapes by controlling the mechanical strength and resistance of rock formations to weathering agents. Differential weathering along joint planes contributes to the formation of cliffs, ridges, and other landforms. Geomorphologists investigate the role of joints in shaping topographic features, sculpting river valleys, and controlling the distribution of sedimentary deposits. Understanding how joints interact with erosional processes helps unravel the geological history and evolution of landscapes over geological timescales. In summary, the consideration of joints in geology spans various disciplines and applications, from structural analysis and engineering design to hydrogeological modeling and hazard assessment. By integrating joint data into geological investigations and decision-making processes, scientists and practitioners can better understand the complex interactions between geological structures, natural processes, and human activities, ultimately enhancing our ability to manage Earth's resources and mitigate geological risks.